So our next speaker is Gautham Narayan. He's the Lasker Data Science Fellow at Space Telescope. He got his PhD working on Type 1a supernovae from Essence and Pan-STARRS at Harvard. He did his first postdoc at NOAO in Tucson as the lead developer of the Antares project to apply machine learning to time domain alerts from Zwicky Transient Factory and eventually LSST. And he also works with several folks at Space Telescope on high-precision photometric calibration for cosmological surveys. So he's going to be talking about probing supernovae progenitors with early-time light curves from K2.
Great. I hope you can all hear me. So this is work that I've been doing with a whole bunch of people as part of the KEGS project. These are the Kegerators. I want to particularly highlight Armand Rest, who is my effective thesis advisor in many ways, and has been sort of a mentor to me through my grad school and as a postdoc. So we begin here with, we've been studying supernova forever, right? This is an image from Kepler's own notebook in 1604, the Stella Nova in Pare Serpentare. And down here, this little thing marked with an N, that's his observations of a new star, a new nova. All of the supernova between 1054 and 1881 form 1 second on this slide, one single frame. We've used a whole bunch of observational resources over the year, and we found several tens of thousands of these things. Massive amounts of data have been collected on these things. And yet, here we are in 2018, and I would say that we understand the progenitors of fewer than 10 of these. Well, I can count them on my fingers. This is kind of embarrassing. But we're not completely clueless. Theorists are always at hand and can give us some models, and their models look kind of like this. They broadly fall into two categories. Either there's one white dwarf, two white dwarfs in the case of a type 1a supernova, and somehow the other is getting mass onto it and reaches the Chandrasekhar limit or near there, either from a main sequence star or through in spiral with another white dwarf. And so these are the two different progenitor channels you have. And then to confuse things further, you can choose different explosion mechanisms for how the white dwarf blows up once you've added the mass to them. So the real picture is basically pick something to go along with the carbon-oxygen white dwarf, pick something somehow to start the flame inside that carbon-oxygen white dwarf, and then you get something that looks like a supernova out. And people have done this with Chandrasekhar mass models, sub-Chandrasekhar mass models, super Chandrasekhar mass models, and have spent several hours on computer simulations. So you should not be surprised to know that basically any of these things produces some kind of stellar death explosion. Now, of course, they have several differences, but the challenge is, as the theorists have been coming up with new models, we've been finding new kinds of supernova that fit those models just fine. So we haven't really effectively found something that can tell us clearly what the progenitors of type 1a supernovae are over here, mostly because every time we find something new, a theorist comes up and says, well, I have a model that fits that. And so you can put these things on a grid of whether you have single degenerate or double degenerate, and whether the flame starts off subsonic and goes to supersonic, or whether there's two different detonations or merger scenarios, and each of these replicates some part of that diagram, the previous slide, and whether the system is sub-Chandrasekhar or super-Chandrasekhar or a Chandrasekhar mass white dwarf. So we're not learning a great deal from the full explosion, but where we are really sensitive to the explosion physics is at early times. That's the sort of a key time regime where we can hopefully distinguish between the different kinds of progenitor channels that we have for type 1a supernova. So Dan Kaysen in 2010 wrote a really wonderful paper where he showed that there should be an excess of UV flux from the ejector of the supernova plowing into the companion star. And how much excess you see depends on the mass and the radius of the star, but also on the viewing angle. And so for something like a red giant star, you'd see a very, very significant excess flux, and it's weaker in the V band. So this is a clear observational signal that we can go look for and try to distinguish what the different progenitor mechanisms are. And there have been fortuitous discoveries of supernova within the Kepler program. So back in 2011, we found one of these objects, KSN 2011b, and Kepler produces really beautiful 30-minute cadence data for supernova while it's looking for exoplanets, and we can identify exactly where the explosion is and look for any kind of flux excess from those KSN models. And this particular object really didn't seem to have anything of that nature. Kepler was a beautiful experiment producing useful supernova for us. These things could go onto Hubble diagrams. The Kepler supernova are typically a little bit fainter and found in red galaxies just because of where Kepler was pointing. There was also interesting type 2p supernova, and you could really see things like a shock breakout from these things, interaction with stellar winds. And so there's, in fact, another paper in preparation by Brad Tucker about these in the next couple of, hopefully later this year. Newer models of these things have suggested that KSN 2011A has a blue supergiant companion, or is a blue supergiant, whereas KSN 2011D is a red supergiant. So at least on the type 2p front, we're learning things about the progenitor system from this really high cadence Kepler data. And we have something like 4,000 observations per object. So this is a really wonderful system. And we're getting this sort of for free, fortuitously from just Kepler's observations. So things are really interesting at this point, right? Where we don't have any ground-based facility that can give us cadences like that. And then the reaction wheel broke. The wheel comes off Kepler, it said, and if you look at the members of the Higgs team, their faces look a little bit like that. And so we're all very sad. But meanwhile, back on Earth, things are getting interesting from ground-based observations. So this is a beautiful image of M101, which hosted a supernova 2011 FE. It's this thing down here. Most of the time, supernova pictures come with a helpful arrow to tell you what it is, but occasionally you just have to know. And because of the deep imaging that we had for this galaxy and all of the previous imaging that we had, we could say that there was no greater than one solar mass companion there at that location. Curtis McCulley worked on 2012Z. This is HST ACS imaging, and here this is this underluminous supernova. And we could tell that there was a helium donor companion for this particular object. So here is a white dwarf gaining mass from something that is not another white dwarf, but it's an underluminous supernova. It's not a regular type 1a supernova. Yi Kao worked with IPTF on 1480G, which is another underluminous supernova, again showing there was some kind of UV flux excess here, and again potentially indicating possibly a red giant or a main sequence companion. And very recently, in fact, if you were at Andy Howell's colloquium last year, you saw this object. This is 2017 CBV by Griffin Hossanzadeh. And this early time rise of this type 1a supernova, again, seems to show some UV excess. It's not very strong. It's weaker than it should be if it was really the shock excess from the KSN model. And more confusingly, the nebular phase doesn't seem to show any excess H alpha or helium like you would expect if there was shock running into a star. But it is sort of interesting that we're now starting to see more of these things from the ground. So what we really want is something that's like Kepler, dedicated to finding supernova and getting us beautiful light curves like this. Well, it turns out that Kepler works just great in 2-gyro mode for transient community. Smart people realized that you could balance the solar pressure to keep it pointing in more or less the same direction. And this wasn't great necessarily for the people who are looking for exoplanets around other stars, but works great for supernova and gets you these 30-minute cadence light curves over 100 square degree field of view. The original K2 mission sort of had 500 galaxies in it, but the K2 campaign lets us search something between 2,000 and 14,000 galaxies in every single 80-day campaign. Now, the first 15 campaigns were all forward-facing, which means you can only really observe them in a small window around twilight. So they're not necessarily the most effective thing for finding supernova because you can't really go follow them up with ground-based resources. But nevertheless, people tried. So this is a spectrum that Steve Margheim took of one of the very first objects. It was observed at MRs of 2.5 at, I think, minus 14 degree twilight. So really pointing Gemini almost at the horizon to get, some signal. And sure enough, you can see these supernova bumps and wiggles. So Kepler's back in business. We can go to hunt type 1a, right? Then we found this weird thing. This is a paper that Arm and Rest put out earlier this year. This is not a type 1a. That's a type 1a up here. There's a blue curve. This thing rises much too fast, 2.5 days, and drops off in sort of six and a half days in a bit. It isn't really a point 1a. It doesn't look like a kilonova. And so our best guess for what this sort of thing was a hypersonic shock breakout from an extended dense medium, if I remember. It's not really consistent even with other really fast transients. 2002 BJ and 2015 U. But again, it's not a type 1a supernova. This is just something that you get for bonus. Campaign 16 and campaign 17 changed things around a little bit, because where the rest of the campaigns were forward-facing, these two now point the other direction, or maybe another backwards. This one was forward-facing, and the other one's rear-facing. Anyway, the point of this, this changing the direction in which Kepler is facing, is nicely illustrated in this wonderful cartoon, which says, hey, look, the Earth can get these spectra because you're looking at the same stars and galaxies at night. So this is something Alex Cody put together. And while the Beehive cluster is a big part of the field in campaign 16 and 17, there's all of these wonderful supernovae over here at high redshift that we're suddenly being able to get at. So campaign 16 and 17 were focused on these extragalactic transients, and it started becoming kind of like Christmas. We've started finding these things and putting out ATELs really, really rapidly, and the numbers just grew. At one point, I remember last semester, I got an email from Arm and Rest being like, come in now, we have to get this on TNS now. That's cool. That's when the project's actually working. The greatest thing that we've had, I think, was collaboration between several different affiliated groups. So there's observations from Pan-STARRS using DECCAM that Armin leads, SWORP from Ryan Foley's group, the Atlas team in Hawaii, Assassin. Several facilities are really dedicating resources to Kepler follow-up. And so this really serves as a kind of a model of how to manage follow-up with scarce resources for particularly interesting targets for people who are thinking about what will we do when the next kilonova goes off. Have a benevolent dictator like Armin who says, I will punish you, and gets things going. One of the really interesting objects we found was 2018 OH. This is a supernova at relatively low redshift, and it's vanilla, normal supernova, slightly bluer colors than usual, and has some carbon absorption, indicating there's some unburned material in the explosion, up to about 3 weeks past maximum, but otherwise looks like a perfectly vanilla, normal supernova from the ground. But if you look at the Kepler light curve, and the Kepler observations here are these gray dots, those are actual points, there's not a line going through things, and you look at the really, really early time of them, and you compare the observations to a t-square fit that you would expect from an exploding fireball, you find a very clear flux excess. That's pretty cool. That's really interesting. This is the sort of thing that might be this shock signature that Dan Kaysen suggested back in 2010. And now, of course, we looked at 2011b, and we didn't see any flux excess there. So did we do something wrong? The answer is no. We had enough signal to noise back then as well, and if you adjust these two supernovae back to have exactly the same light curve shape, even relative to 2011b with the same light curve shape, there is clear excess flux. So if it had been there in 2011, we would have seen it. This is probably a viewing angle effect as to why we didn't. Or maybe these things just have different progenitor systems all contributing. So this excess flux is real, and the question now is what the source of the excess flux is, and there are, of course, several different models, because theorists have a field day with these things. So this collision with a binary companion, this might be just some nickel-56 mixing going on, there might be circumstellar matter interaction, or this might be some kind of double detonation signature. It's hard to tell with just the Kepler data, because there's only a single passband. And there have been two different models, two different groups working on this. Georgios Dimitriadis out of UC Santa Cruz and Ben Shapi at the IFA, and they both submitted their papers on this. And it turns out that a lot of these models all are pretty good at modeling the supernova flux if all you're looking at is the Kepler observations. But as soon as you start to add color information from the ground, what happens is this collision model, where the shock is plowing into a companion star, starts to be a little bit favored. There are different ratios for nickel-56 mixing, and we can't completely rule that out as yet. But this is clearly more favored than the other two scenarios here, and that's sort of interesting already. We're sort of learning at least something about the progenitor system here. There's another interesting object, 2018 AGK, that I'm working on, and we're looking at this, again, this really tiny little bit right at the start, just to figure out whether this thing is showing an excess shock signature or not. Now, if you look at this light curve, you'll see all sorts of nasty dips and sawtooths or jagged patterns sort of superimposed on the supernova flux. These are systematic effects with Kepler that we're cleaning up. I've until now sort of tried to make it seem like Kepler is just this gift that keeps on giving, but it is a complicated reduction problem. The really cool thing about this object is it's a little bit further away than 2018 OH, and we just got lucky and happened to have like 10 decam observations at really early times. So we're working on removing these artifacts, and hopefully we'll have an analysis of what this object is and whether there's a companion star to it a little bit later this year. Those artifacts that you saw in that light curve, they come from some of the fun effects with Kepler because, like I said, there's only two reaction wheels, and it's balanced by the solar pressure. Every now and then Kepler has to fire its thrusters to get itself back in position. And so as you download the pixels from Kepler, you'll actually see the object move around within the frame from different points to different points. There's also this rolling band effect where periodically there's just a decrement in the flux that just rolls from top to bottom. I don't know if you can see this with the contrast over here. Every now and then you also see asteroids going through your pixels because Kepler is rather undersampled compared to a lot of the ground-based facilities. Still, we can disentangle all of this, and so hopefully we'll have this cleaned up pretty soon. Kepler also is getting us prepared for the test mission. So where Kepler is a relatively small 100 square degree, relatively small already, it's a ginormous field of view, but compared to something like TESS, it's small. The main part of the TESS survey will cover 85% of the sky. This is just great. Right? And at 12th magnitude, we have sort of 1 millimag precision, but even at 17th, it's 5%. That's not bad. You can do a lot of science with that. And this thing will just produce supernova all over the place. We'll have, we'll go from 50s odd objects to 100 very, very quickly. And so we're really excited about this test workshop next year. We'll hopefully be part of that and do some cool science and get ready for finding all of these things with tests. So I want to quickly conclude. I didn't want to take too long on this. K2 has been an amazing facility for transient science already. We've seen supernova with excess flux, regular type 1a supernova showing excess flux at the beginning. We've seen interesting core-collapse objects, shock breakouts, interactions with stellar winds. There's some clearly plain weird things that we also have found and we're working on. These are two objects that students are working on, one at ANU and one at Cambridge. This thing is a shock breakout of a Kepler supernova compared to 1983J here in the colors. And you can see the much more pronounced shock breakout. In fact, the true shock breakout is probably down here. And this is sort of a secondary effect, but it's a very strong signal. And it's really beautiful data to work on. Whereas if you look at the x-axis on this sort of thing, this is really, really rapid change in sort of a 5-day window as to what the flux is. And we have no good idea really what this is. And so we're working on the modeling for that. So there's all sorts of interesting results to come. And we'll have these results well after the mission is done and the satellites are the fuel. But I think taking a step back and looking at the bigger picture, now we're finding things earlier and earlier than ever before. And we're finding things not just in the optical, not just in the electromagnetic spectrum, but also getting signals from neutrinos, we're getting signals from gravitational waves. So this is a really interesting time to live in. Understanding the progenitor systems and the explosion physics will help improve our models of type 1a supernovae and other kinds of supernovae, of course. But it doesn't just end there, right? Because these things feed back. This will let us better standardize type 1a supernova. And in fact, people here at Space Telescope, Brian Hayden and Dave Rubin, have been working on, can we add a second parameter to describe type 1a supernova, and this seems to have some sort of effect on the rise time. So that's an interesting potential future avenue of research that we can extend Kepler data to. JWST coming up will give us a lot more near IR information. The dust has less of an effect, and type 1a supernova also just happen to be more standard. They're better standard candles in the IR. All of this will mean that we can measure the equation of state of the dark energy, which I've carefully avoided mentioning until this point, much better with LSST and WFS. So this is not merely an astrophysics experiment, but it has just wide-reaching consequences for, I think, physics in the 21st century. I think it'll be a really interesting time. So if you're a grad student and you want to come work with us, I'm on the 4th floor, as is Amin, and we'd love to chat with you. Thank you.
Thank you. And Gautham.
All right, nice talk. Was the magnitude of that flux excess as predicted? Do you expect, if you could detect these in a bunch of objects, would there be a range of magnitude of the excesses? And what does that tell you about the relative masses of the companions? Or
Yeah, so there would be a range of flux excesses depending on sort of the mass and the radius, as well as the separation to the companion star, and also viewing angle. So the way people have done this, and the way sort of SDSS looked at this back in 2010, I think actually Brian Hayden led that paper, if I'm not mistaken. I don't know if Brian's here, but he's now at Space Telescope, is to try these things with simulations. A lot of the surveys, especially the ground-based surveys, they have relatively poor signal-to-noise data at early times, and so you really have to look at a stack of a lot of these things to see whether you'll actually detect something. So what people do is simulate regular type 1a light curves, add in some flux excess to the simulated light curves, go through the stack data and see what's ruled out and what isn't. And so what we can rule out already pretty much is a companion star that is a supergiant. And I think, if I remember right, companion stars that are sort of larger than 6 solar masses are also ruled out or strongly disfavored. They can't have a very large contribution to the single degenerate channel. And I don't know what this is in magnitude space because we don't really think about them in those units, but it's usually the flux excess is sort of probably on the realm of like, a half mag, maybe even less at these early times. And if we were seeing much more than that, we would very quickly say, well, the companion can't be a main sequence star, it must be something bigger than that, or there's just some other mechanism at play.
Okay, I have more questions. Irene?
So I guess hopping on to that, this is also a great talk. But how do you, aside from figuring out the different, whether it's a supergiant or less, these broad swath classes, is there degeneracy within those subclasses, and what other information could you possibly add to help break that degeneracy?
Yeah, there is degeneracy in the subclasses at early times, but as long as you can see the light curve evolution as you go on, you know the sort of broad class of the supernova, and you can look at things at nebular phases once the supernova light has faded. So, for example, if you were convinced that something had a main sequence star or a red giant star as a companion, those stars will survive the supernova explosion. They'll be weathered by the fact that you just blew up a thermonuclear star next to it, but they will survive. And so you can wait a couple of years and go point Hubble at it and go get really deep limits on whether you can see something like that or not. We normally know their positions well enough to do this, and people have done this. And so you can break the scenario, degeneracies in that scenario as well. You just have to wait patiently.
Thank you.
And Shanji, you have a question?
Hi, it seems that there are some data before the explosion, right? So what can we do with that data, and what can they tell us about the progenitors?
So the data before the explosion is typically just measurements of how bright the sky background is, essentially. You're not really seeing the white dwarf. The white dwarf is something like 30 magnitudes fainter than the supernova. explosion. So you're never going to see that below the sky. The question is, of course, can you see something about the companion star at the time? With high-resolution imaging from, say, HLT, if you had ACS or 3D pre-imaging, then sure, you can go look for the companion star and see if you can actually see them on the pixels. With Kepler, not so much, because the pixels are just effectively too big. You can't really tell what stars are at that location. So really, what we use that quiescent period effectively for is to set a baseline for what the flux is and use that for the absolute calibration.
Any more questions? Okay, well, before we all go, and before I thank all the speakers, I'd like to thank the HotSci team, so Lauren, Leah, and Claire, who aren't here today, and also Jen for running around with the mic today and doing WebEx, Andy, and all the AV and the ADV team, and also admin people such as Martha for kind of making this a big success. So this is the last HotSci, so join us for CoolSci in the winter, and let's thank all of our speakers again today and everyone that's helped.